Hi everyone. This video is an attempt to get those who are more knowledgeable explain to me how this is working actually. Right now I have my toroid with the magnets adjusted to match the exact inductance of this huge coil here, which is a full spool of 14 gauge magnet wire that is spooled in the way where you create what's called a Brooks coil, which is wound to obtain the highest possible inductance. So this is a 11-pound spool of 14 gauge, I believe is the correct gauge, of this magnet wire, and it has about a 4-inch air opening here at the center. So there's a cardboard tube that was in there, and a Brooks coil, it has to it's not very wide this way, it's more concentrated. This dimension is about twice, or the center opening is about twice the dimension of this dimension here. Anyways, it has the highest inductance it can, and that was an experiment to verify the if it does in fact change the inductance, and that experiment was successful, and the spool itself was about if I remember, it was around 75 millihenries. And after I spooled it, the same wire, this way here, it was 113 millihenries. So remember, it's an air core. There is no core inside. There's just airspace there. So, and the total DC resistance of this coil here is exactly 5 ohms. Perfectly bang on, 5 ohms. And the DC resistance of my little toroid here is exactly about 6.95 ohms. So you can nearly call it 7 ohms. So this one has an extra 2 ohms of DC resistance maximum than this one here. So I have my inductance meter attached to this little toroid here, and if we turn it on, I've tuned the magnet so that I have 113.6 or 0.5 roughly of inductance there. And what I'll do now is detach these from that, and now I'll attach it to the very large coil there, and we'll check its inductance. So as you see, I've got them perfectly matched. So the next thing I'm going to do here, so we've got two coils, one an extra 2 ohms, but both identical in inductance characteristics. Now what I'm going to do is I'm going to connect my little toroid here to my MOSFET, which by the way is already running from the signal generator here, and that's what's switching the gate at this time. And I connect my positive lead here to the coil, and we're utilizing 12.87 volts from this feed battery here, and this meter, my quality meter, is measuring the voltage across the resistor there on top. And I've got it tuned to actually, you know, go into the negative, sending back energy, all right? And so it's at its best setting there for that 12 volts and that particular inductance and all that. What I'm trying to do here is understand this effect better, and looking for answers. So here is our waveform. I've stretched it out as much as I can here. That's our pulse here from the single generator going to the gate of the MOSFET, and here we are with the sine wave that's happening with the you know, it tuned to that preferable setting. And at that inductance, it will resonate at 14, well, might as well call it 15 kilohertz. And we're getting 29.22 peak to peak, about 10.31 volts RMS across it. And there's our peak to peak voltage of the trigger to the MOSFET. Now that's my MOSFET that can work with a 2-volt trigger, 1 to 2 volts, they say on the specs. So we're definitely triggering, and definitely the scope probe here, the green one, is across the source and gate. And the other probe here is, where is the other probe? Oh no, okay, so this probe here is between the source and gate, the green one. And this one here is at the gate, just measuring the gate, basically, the pulses from the signal generator. So, you know, as you can see, you know, if I connect it or disconnect it, everything goes away. I just pulled off the connection here, gone, and our, you know, meter here goes back to 0. Alright, so connect it, our pulse is back, and our meter goes back into the negative. Now, if both inductance are the same, and this one has less DC resistance, you would think that this coil here should perform the same way. We've measured the inductance, both are tuned exactly the same. Now let's connect this coil here and see what happens. So we now connect our positive lead to there. Take this one out here and connect this one in here. And now we have a completed circuit. So if we look at our meter, that's what it's using, but that's not truly what it's using, because if we look at our waveform, we're not getting anything. So there's a very different interaction. I haven't changed a single thing on the signal generator. Looking at this, to me, that is basically the gate is not receiving enough voltage to trigger this coil to get activity. So what I would do is I would increase the gate, so that, you know, that's what I'll do here. I'll increase the voltage of the output of the signal generator, which was tuned for this coil, for it to do its thing. So now I'll tune that and I'll show you. So what we'll do is we'll tune it, increase it, so that we get the same size waveform there that we had before. Alright, so that our peak to peak is back at 29.22. Alright, let's try and get that. Okay, close enough. So this is what we have now. Same frequency, we're at 28.91 and at 10.31. And, you know, that's obviously held. Now, if we look at what current we're using, then that's what we're using. We're using now 588 microamps. Now, why is it? Why is this coil not capable of doing the same thing? Why is there such a difference? I would like to, you know, receive answers, if anyone understands why there would be such a difference between two pieces of wire that are very close to the same DC resistance. And this one actually should be worse because it has an extra close to 2 ohms than this one. And when this one is connected at the same frequency and everything, it can't even get triggered. And I kind of know why it can't get triggered, and I'm not going to share that, but you know, obviously it has to do with the resonance. Once things, I guess when it starts getting to resonance, it's more efficient. Anyways, please post your comments and be interested in hearing what you have to share. Thanks for watching.